Hi all, welcome to another video of the video lecture series for the subject compressible fluid flow. In the previous video, we have discussed in detail about certain thermodynamic relations and concepts which will be very important when considering the compressible fluid flow analysis. And also those concepts and relations will be very helpful for the derivation of rate equations for control volume in the case of compressible fluid flow. And what are these rate equations? And how these rate equations will help in analyzing a compressible fluid flow. Let us see what is a rate equation. Here, laws of conservation of mass, momentum, energy, and entropy. They will govern the equations of the compressible flows. So the equation for mass, conservation of mass, equation for momentum, equation for energy and entropy. These are considered to be rate equations. We already know these terms. We have already studied about these terms in our previous semesters. But all those equations and all those concepts were considered to be on the basis of incompressible flow or like that. Now, as our concentration has changed, we are now concentrating on compressible fluid flows. We need to change this equation. We need to change the nature of this equation of like the laws of conservation of mass, momentum, energy, and entropy. These equations will have a considerable change when we are dealing with a compressible fluid flow. Now, let us see what all changes will come to these laws or equations. And these conservation laws are well explained for a system. In the case of a system, we have already discussed about system and control volume approach in the last class. Now, we will use the same concept here for the derivation of rate equations. Now, we will be first deriving continuity equation, which is otherwise known as conservation of mass. As per the continuity equation, we are considering the continuity equation for steady and unsteady flow. And as per this law, it states that the mass can neither be created nor be destroyed. Okay, we already know that. And here, the equations based on these laws we will consider these laws for a flow through control volume. Okay, that is the main difference. Now, check this scenario. In this diagram, we can see a flow is taking place, and these arrow marks and these lines represents stream lines. Okay, so the flow is basically taking place from left side to right side, and 5 stream lines are shown here, and a system is considered. This oval shape represents a system at time t. So here we are considering system at 2 instances. So just think that at time t, the system is at first instance. Okay, this thick oval shape shows that the system is at time t. It is the first instance, and after some time, after a time dt, if dt time has passed, the system will reach to another instance where system at time t plus dt, that is represented by these dotted lines. Of course, it is an oval shape because it is having the same mass as before. Mass is not changed. Mass is conserved as per the law of conservation of mass, but its position has changed. Now, we already know that system can be fixed or moving. So here our system is moving. It is moving from left to right. Its first position was at time t. It is shown by the thick oval, and after time t plus dt has passed, the system has reached its new position. It is represented by this dotted line oval. Okay. Now, by considering this two systems as at 2 instances, we can divide these 2 systems into 3 regions. Okay, so first region is common between these 2 instances, that is shown here as 1. So region 1 is common between system at time t and system at time t plus dt. And there is a region 2 which is exclusive for system at time t plus dt. Okay. Similarly, there is a region 3 which is for the system at time t. So there are 3 regions. Now, when the system approach, now the concept of system and control volume is considered. Here, the region 1, we can take the region 1 as a control volume because it is common to both the instances. So technically it is a fixed position. The region 1 is we can consider it as a fixed region because only 3 and 2 are moving, but the fixed region 1 is can be considered as a fixed control volume. So here throughout the derivation of this equation we will consider the region 1 as our control volume. Okay, so the control volume has a control surface also, so just consider that. Now moving to the derivation, starting of the derivation, we are applying law of conservation of mass to the above system. We are again considering the diagrams. So at instance number 1, at the first instance system at time t, we have two masses, the mass in region 3 and the mass in region 1. So their combined mass will be mass 1t, that is m1t. 1 represents region 1, t represents first instance, plus m3t. 3 represents the mass of the fluid or gas, liquid or gas in this region 3, and t represents the instance. So m1t plus m3t will be the combined mass at in the system at time t. Similarly, after time dt has passed, our new mass of the system will be m1 t plus dt, that is the mass of the system in region 1 in the second instance, t plus dt instance. So m1 t plus dt plus m2 t plus dt, but the combined mass will be same as before because we are considering law of conservation of mass. The mass will not change, that's why we are equating these combined masses in both cases. Now we have rearranged this equation. That means we have taken the m1 terms to the left hand side and all the other terms to the other side, and also rearranging and dividing throughout by dt. We can write the expression like this. Okay, here we have taken m1t plus dt as a positive value, so m1t will be negative. Similarly, m3t will be positive and m2t plus dt will be negative. We have rearranged like that. Okay, now we will take the left hand side and we have applied limit to left hand side, that is limit dt tends to 0. That will give the mass of the control volume. Okay, the change in mass within control volume in partial derivative. So after applying the limit, this expression will convert to dou by dou t of mcv, because we have considered only the mass in the region 1 in both instances in this left hand side term. Okay, so applying limit we can get the mass of the control volume in partial derivatives, dou by dou t of the mcv. Now similarly we need to change the right hand side terms. So we will consider m3t by dt, this expression, and we are changing that expression to sigma dm3t by dt. By sigma dm3t, it means that m3t is actually the total sum of the instantaneous change in mass. Okay, instantaneous changes denoted by dm3t. So the total change will sum of a total change will give the m3t. Okay, this can also be represented by integral value. So here integral, inside the integral we can see that mass, it is mass flow rate, it is represented as mass flow rate, since as per the unit here we have divided the mass with time. So in right hand side also it will change mass by time, it will change to mass by time, which is the mass flow rate. Okay, so this m3t by dt will be the integral of d m dot. M dot will be mass flow rate, and we can see that this region 3 is before the control volume. So actually from the region 3 the flow is taking place towards the control volume. Okay, so the flow is taking place into the control volume from region 3. So we can consider this term as inflow of mass flux. Mass flux means mass flow rate. Inflow of the mass flow rate, because it is taking place into the control volume, that's why we have named it as inflow of mass flux. Similarly, we can change this term also, m2 t plus dt by dt, by changing in a similar manner as before. So that will be equal to integral outward dm dot, which will be termed as outflow of the mass flux. Okay, because region 2 is after the control volume, so mass will be coming from, or mass will be coming outward of the control volume to region 2. So in region 2 it will be outflow of the mass flow rate or outflow of the mass flux, which is represented in integral form, integral dm dot outward. Now we will substitute all these changes in our basic equation. This is our basic equation m1, yes, this is our basic equation, m1t plus dt minus m1t by dt is equal to m3t by dt minus m2t plus dt by dt. We will substitute all the expression by our new expressions, changed expressions. So after substituting, we will get it as dou by dou t mcv is equal to integral forms of inflow and outflow. Okay. Now we can state a concept from this equation like this, that the rate of change of mass within the control volume is equal to the difference of rates of flow of the incoming and outgoing masses, which means the rate of change of mass within control volume, that is dou by dou t of mcv, is equal to the difference of rate of flows. This is actually taken as a difference of rate of flows between the incoming and outgoing masses. Okay, so that is a statement which can be derived from this expression. Now the equation can also be expressed in another useful form. We can also change this equation in terms of density, so that we can finally get to our continuity equation form. For that purpose, we know that mass is equal to density into volume. So here the dou by dou t mcv equation term can be changed to dou by dou t into integral control volume rho dv. This mcv is actually rho into volume. We can convert that into integral form. For that, we need to consider integral of the control volume into rho into dv. Here the differential is taken for the volume, so rho dv. The unit is same. Here the unit is a kilogram. Here also the unit will be coming to kilogram, because it is density into volume. Now this can again be changed like this, integral cv dou rho by dou t dv. Okay, we have taken this partial derivative to the inside of the integral. Here rho dv is the elemental mass in the control volume corresponding to infinitesimal volume dv. Now this outward and inward flow, we need to change that also. For inward flow, integral dm dot, we have changed mass flow rate into density into velocity into area. Mass flow rate can be expressed by density, velocity and area by this expression. So integral inflow dm dot will be integral inflow rho cn. Cn is actually the velocity of the fluid velocity normal to the area considered in the control surface. Okay, we can see that in the diagram in the next page. Integral inflow rho cn dA. Similarly, outflow can also be written like this, integral out rho cn dA, where cn is the velocity of the flow outward the control surface. Look at this diagram, you can see the cn velocity. Here the control volume is here, and we have considered a control area, control surface on the control volume, and on that control surface the normal velocity is cn, so we have taken that velocity component. Now substituting the equation, the new forms of the equations are substituted in the previous expression. Now the integrals on the right hand side of the equation represents the integral quantities at entry and exit. And also we can change this inflow and outflow like this, because their entry and exit we can give notations like 1 and 2. And we will also take the vector notation. When we are taking the vector notation, there will be a negative symbol. Okay, and the vector notation will be taken as surface integral. That's why this symbol. The remaining portion of this derivation will be taken in the next class. Thank you.